Okay, folks, so I want to look at one last example, and in some ways it's going to be an easier example, in some ways it's going to be a more complicated one. So first of all, notice that rather than being given a function, some f of r theta, we're asked to compute the area inside a region. And so what do we use as our function then when we're working inside of that, when we're just trying to compute the area? We use the function 1. And we saw that before in the rectangular coordinate system. And the way you can think of that is if we take in the polar plane with the z-axis coming out of here, so pretend this is our polar plane here, I guess. If we took some region in the polar plane, and then we looked at the function that lies above it, the function 1, then this function would just simply be a shape that looks like this. And so if we were to compute the volume of this shape, notice the volume of this shape is just the base area times 1. And so when we compute the volume of the shape, what we're really just computing is the base area. We're computing the area of R. So we're going to be using that function again here in this problem. So in that sense, it's going to be a little bit easier to deal with because we don't have some messy function that we're trying to integrate, at least off at first step. The next thing is we have to decide our region here, and this is where this is a little bit trickier. So here's our polar axis, okay, P, and we're going to go ahead and sketch the graph of 1 minus cosine theta and 1. I find it easier to think of this as sitting on top of the rectangular coordinate system there. It just gives me a little bit more to reference. And we sketch this graph r equals 1 minus cosine theta at the beginning of this unit, or at the beginning of this section. And if you recall, you could build a table of values. You could pick theta values here. When theta was 0, the radius we found was 0. When theta was pi over 2, we found the radius was 1, so that gave us that point up there. And when theta was pi, we found that the radius was 2. And when theta was 3 pi over 2, the radius was 1 again. So anyway, the graph of this we saw, and if you want, just go back and look at one of your earlier graphs. I think it was maybe question number 3 on this. We saw that this was the shape of this cardioid here. So that's the graph of our r equals 1 minus cosine theta. Easier to graph is the graph of just r equals 1. That's just simply a radius, or sorry, that's simply a circle with a radius of 1. And so let's see here. Here's maybe 1, here's 1. So we sketch this circle. Here we've got the circle of radius 1. Then what are we trying to find here? Well, we're trying to find this area in between the two curves. Okay. So we're doing a few things for the first time in this problem in our polar coordinate system. The first thing is notice that if I think about this region being bounded between r equals 0, which is the pole, and some outer curve given by some other radius, we can see that at some point we change over. Notice here, always the pole is the lower curve, but the upper curve starts off being the blue cardioid, and then switches over to being the red circle partway through the problem. So when we go to set this up, we're going to say that we're looking for the double integral over our region R. Normally we'd write our f of r theta, r dr d theta, but in this case, because we're looking for the area, we use the function just 1. So we're looking for the double integral over 1 of r dr d theta. And this will be the last time I write that 1. But the next thing I want to see is that I have to break this up into two regions, similar to what we did in a similar problem in the rectangular coordinate system. Oh, and I said I wasn't going to write the 1, and I guess I did. So what do I mean by these two regions? Well, one way to look at it is we've got, let me see if I can sketch each region separately. We've got the first region, which is going to look like these two parts, kind of the bumps of the cardioid. That's going to be the first region that we find the area of. And then the second region is going to be the circle, the half circle, and that'll be the second region we find the area of. So I'm calling this first region here R2, and the second region, or sorry, we'll call that first region right there R1. That makes more sense, and call the second one R2. Okay. So again, I first had to sketch these two curves. And sketching r equals 1 wasn't too bad, but sketching this cardioid required a little bit of work, but we did that work in an earlier question. And now what I'm doing is I'm taking this entire blue shaded region here, the region that I've shaded light blue here, and I'm breaking it up into two different pieces. The part where, notice in all cases we're thinking about a radius extending from the pole outward to a curve, but notice that for the part that I've labeled with R1, the curve that we stop at is this blue curve right here, which is given by r equals 1 minus cosine theta. Whereas all through here, as I think of these radial arms extending outwards from the pole to this boundary curve, the boundary curve r equals 1 in red here, this has a different upper curve. Okay, so now we're ready to go ahead and give the integral here, and we're not going to evaluate this one. I'm just going to set it up. So for region 1, I want to take theta values. I want to make sure I capture this region here and this region here. So I'm going to do my theta values ranging from minus pi over 2 to theta equals pi over 2. There's probably other ways I could do this, but I think this is the most systematic way to make sure I capture this whole region here. So I think of, I've got a radial arm extending out here, and that's at what angle? That's at theta equals minus pi over 2. I have all these other radial arms extending outwards. That's at theta equals 0, and then they keep extending outwards. And then we stop right here at theta equals pi over 2. Okay. Now we've got to decide what are the actual outer and lower curves. Well, so in all of these cases, I've said we think of the radius as starting from the pole. So in all of these cases, the radius is going to start from 0. And then we extend outwards until the radius hits the blue curve. Well, that means the upper curve there, in a sense. I mean, this doesn't really look like an upper curve as it did in the rectangular coordinate system. But that upper curve is r equals 1 minus the cosine of theta of 1 r d theta. Then for the second region, this is the region that I've labeled R2 that I've shaded in red here. So if we think about when do I first start drawing the radii? I start on this side here, and then I've got a radius, and then I stop drawing radii when I get down to here. So it seems to me that one way you could represent this, and there are other ways, folks, but probably the easiest way, is to say that the radius we start constructing the radii at theta equals pi over 2. There's where theta equals pi over 2. There's where theta equals 3 pi over 4. There's where theta equals pi. There's where, etc. And we stop when we get down to here. And where is that? That's at theta equals 3 pi over 2. Okay. Then what do our radii do? So as far as the radii are concerned, each time I've again started the radius at the pole, and then I've stopped the radius when I hit this outer curve here. In this case, this outer curve is just the curve r equals 1. If this curve had been some other function of theta, I would go ahead and list that there. So it could be, maybe this is the sine of 2 theta, or some other curve that is being traced as that outer curve for our region. But in this case, although we're calling it a curve, it really is just the constant where r equals 1. Again, let's say that one more time. I would start my radii from the pole here and extend outwards. So the radius starts it with a length of 0, and it stops with a length of whatever the value on that curve is. Because that's the curve, just r equals 1, we stop our radii at 1. And then again, we have just the area function, r dr d theta. Folks, I'm not going to worry about evaluating this right now. It's a little bit lengthy. But if you have any questions on how you would go about evaluating that, please let me know. And that's all I've got. Thanks for your patience.